Is my screen is visible, sir?
Yes, sir, visible.
Okay.
Yes, sir.
So,
Please go ahead.
so good afternoon to one and all who joined in today's lecture. So we are in QT-03 uh, 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 series. This is about Saram and myself, Dr. Jayakumar Vaidya Shankar, founder and CEO of Anatandra Private Limited. And we are offering workforce training related to quantum. We are located in Bangalore. So today we're going to explore about Simon's algorithm. So this algorithm is very important. This algorithm provides the first example of exponential speedup over the best known classical algorithm by using a quantum computer to solve a particular problem. So if you want to use in any quantum algorithm, first you need to prove or demonstrate quantum is in certain way exponentially speeder when compared to classical. So this is one kind of algorithm which proved exponential speedup. So that is why Simon's algorithm is a booster for all quantum algorithm whatever we discovered so far. Okay, this is the one of the first algorithm to prove an exponential speedup. So originally, this paper is published in 1994. Simon's algorithm was a precursor to Schwar's well-known factoring algorithm. Okay, and it served as an inspiration for many of the seminal works in quantum computation that followed. So first, I'll try to show that paper for your reference. So this is that paper. This is that paper on the power of quantum computation written by Daniel Arsein. Okay, I'll share this link in the chat box. So if you got free time, you just go and refer. Is my voice audible? I try to increase all my voice.
Yes, sir, you are audible. Quite
Yeah,
clear.
thank you. So go to this link and you'll get to know about So this his work is described by Simon quantum AWS. If you mention, it will lead to this page. And you can see the original author discussed about this paper in this blog spot. So please go to these two web page. One is the original paper and the other one is the description of that algorithm by the author itself. Right. So if you want to understand Schar algorithm, you need to understand Simon algorithm first. Then only you are able to understand in better way how Schar's algorithm works. So he described about his paperwork. I will quote his own term as it is. A bit of amusing history. I submitted my algorithm to a theoretical computer science conference in 1993, but it was rejected. Imagine it is the first quantum algorithm which gave the exponential speed theoretically proven. Okay, but the panel members in the conference not able to recognize its potential, they rejected this algorithm. So sometimes if you are publishing any one of our paper to some conference or journal, most of the time we'll get rejection. It doesn't mean your paper, your concept is somewhat weaker or not contributed, but the panel members not able to realize on the spot. So it will take some time, right? So even for persons like Simon, they rejected. So any rejection for our thought works, we no need to worry. We no need to bother. So this is the best takeaway what I get from this paper. However, one of the author, Peter Shaw, was on the program committee for the conference and immediately saw that potential. So, what is the key takeaway? A person who is working in the same domain, they able to look out to your perspective, they able to recognize what is the potential of your work or idea. If such kind of person are there, they able to recognize your work and they able to accept. Okay, so most of the time it won't happen because the panel have a diverse member of committee. So let's hope for the best. So what is they can apply the same general algorithm structure to concentrate problems like factoring and discrete algorithm. So whatever Simon proposed, it is very, very generalistic idea. But what does Peter Shaw think about? He want to implement the Simon's idea for a particular problem like factoring and discrete algorithm. So I hope this algorithm will give a better understanding about all these perspectives. Okay, and let's see what he tried to convey in both terms. After trying unsuccessful submit, both Daniel Simon and Peter Shaw resubmitted their work in upcoming conference after that. So we need to submit our works. In fact, they agreed to merge papers if only his paper was accepted, but committee fortunately accepted to both of them and giving us credit for our respective portion of resulting achievement. Okay. So what happened? If one of the paper is able to accept it, they try to merge both papers, but committee is generous enough to accept both papers. So sometimes it will happen. So we need to submit our paper in multiple venture in order to get selected. So we got so each and every research work we may consider like a process. Okay, and let's discuss about this algorithm. This algorithm solves a promise problem. So it is like a promise. Okay, a function is provided in the form of an oracle that has particular promised property, and the algorithm extracts some related property out of the function, provided that promise is fulfilled. So it is basically a promise problem that algorithm will promise to do something, right? It contains some property in order to do that. So this is the natural target of quantum algorithm because if you want to implement quantum parallelism, it will allow the functions explored across exponential space of inputs. So this is very crucial factor because in classical you cannot access exponential space of inputs. So we have very limited amount of inputs to process, but in quantum it is possible. So according to Simon, Deutsch and Josa were the first to suggest this approach to demonstrating a gap between quantum and classical algorithm, but their attempt, while exponentially faster for quantum algorithm than for deterministically classical ones, is in fact easily solved with the exponential small error probability by classical probabilistic algorithm. So if you look at all these algorithms, only the Simon problem gave exponential speed up when compared to Deutsch and Josa. Okay, so now we are able to discuss Simon problem in detail. So it is a slightly more complicated black block problem involving functions. So all of us know what is a black box. So black box contains some function. We don't know how it behaves, how it works. We need to give some input. Then based upon the output, we are able to judge what type of function it is. So that is why the function of black box, we don't know how we do operation. Suppose if function f tends to 0, 1, it contains binary string 0, 1 up to n number of combination. and this function will reproduce output as 0, 1, which belongs to n number of states, n number of bit strings. So this is a black box problem. Whatever you are giving a binary input, it will produce certain amount of binary output. Okay. This problem is very, very interesting for two reasons. So classically, it will require exponentially many queries, even for probabilistic algorithms, that the error with probability less than or equal to 1/4. Where for an example, I need to give a difference between classical and quantum. You may divide into uh, two topics. So make it this side classical, make this side quantum. Right. So classical is deterministic. Classical system, normal electronic computer always do deterministic computing. Okay. So in quantum, it will do probabilistic computing. Probabilistic computing. For an example, if you are writing a problem, 2 plus 2 in Python, consider this example. The input is 2. The first input is 2. The second input is also 2. And what is the process you are doing? You are doing addition. And what is the output expected is 4. Okay. So if you're writing a program for this, if you're executing in deterministic computing, classical computing, for the first time, you get output as 4 for first time. Number of time execution, consider like this. Okay. If you're running for the same time with the same input, second time, what do you get? Output as 4. If you're running for third time with the same input, you'll get output as 4. Fourth time, you'll get output as 4. So this is about classical computing. But if you do the same thing in quantum computing, first time you'll get output as 4. Second time, you'll get output as 3. Third time, you'll get output as 2. And fourth time, you'll get output as 1. So if you're looking at this, each and every time, each and every execution yields different output for same input 2 plus 2. So this is very weird. Okay. Classical, it is very easy, straightforward. You can easily expect what is the output it's going to generate. But in quantum, each and every time your output varies. Okay. Then how to determine the quantum algorithm, how to believe quantum algorithm? You need to execute for multiple times. We need to execute quantum algorithm for multiple times. Make an example of 100 times. If you're executing for 100 times, then you can see the difference between this output generation. So 80% of time you'll get 4 as the output. Remaining 10% of the time you'll get 3 as the output. Remaining 7% of the time you'll get 2 as the output. Remaining 3% of time you'll get 1 as the output. So if you totally calculate, it will lead to 100%. So each and every time your output varies. Okay. and you can roughly calculate how many times it will do. So 80% of the time you'll get 4. So 10% of the time you'll get 2. And so what is the correct answer? 4 is the correct answer. Correct answer. Remaining these 3 are wrong answers. So after executing 100 times, then finally you need to do measurement. Finally, we need to do measurement. When you do measurement, you'll get only the result as 4. So remaining will disappear. So this is the basics of quantum computing, which is based upon probability computing. Class toward the function, even for probabilistic classical algorithm, you can see even for probabilistic classical algorithm, the error rate with the probability less than 1/4, whereas quantum algorithm can solve this easily. I will try to remove this headset. Now you tell me, is it audible enough? Enough? Is my voice audible enough, clear right now? Okay, much better. Okay, fine. Okay, thank you. I try to reshare. Okay. So if you look at it right way, it naturally leads towards star factoring algorithm. Previous slide, yes, I will go through previous slide. So this is Simon problem, a slightly more complicated black box problem involving function. So we have function which contains input string 0, 1 up to n number of bits, n number of strings, and this function will generate again 0, 1 n number of binary string which up to n number of bits. So very easy for you, right? But we don't know how it process. What is the processing logic behind it? Okay, so Simon's algorithm inspired the work presented in this paper, which is mentioned by Peter Shaw. So in 1995, he put this statement when he attempted CTP conference. So if you understand Simon problem, you can understand Peter Shaw algorithm in better way. Okay, so it is about prediction, about black box function prediction, how it behaves. So this is the simple definition of Simon's algorithm. So a function f of 0, 1 up to n number of bit strings, we're going to generate again 0, 1 n number of bit strings. So it is 2 to 1 for all. If for all a belongs to 0, 1 up to n number of bit strings, there exists exactly one b not equal to a such that f of a equal to f of b. So simply you can put in a diagram. Okay, so this is f of 0, 1. So this is the output generated by that function, right? So here it is 2 to 1. So if there is two objects, it is mapped to one output. So let's say AB, it is mapped to C. Same way, if you have DE, it is mapped to F. So this is nothing but 2 is to 1. Okay. So exactly only one is B not equal to A, and everything it will follow function of A equal to f of B. So we are using this definition to represent our Simon's function. And whenever if you found A comma B, it is a colliding pair. So for namesake, you remember this function. I will try to explain again and again. Okay. So what is the Simon property of this function definition? So it is a 2:1 function with the special property that there exists an R which belongs to 0, 1 up to n number of bit strings such that A modulus B equal to R for every colliding pair A comma B. So this is nothing but bitwise addition. Bitwise addition. So what is the meaning of bitwise addition? I'll tell you example. So consider input A, input B, and if you do A bitwise addition B, which is nothing but binary addition without any carry. So this is bitwise binary addition without any carry. For an example, 0 bitwise addition 0, it will lead to 0. Okay, 0 bitwise addition 1 leads to bitwise addition 1. So 1 bitwise addition 0 leads to 1. 1, 1 leads to 1. So forget about your carry. Sorry, forget about your carry. Actually, it will represent 1 0. So 1 is a carry. 1 is carry. Okay. So what is the given problem? We need to find the black box for f, which consists 0, 1 binary strings up to n number of bits, which will generate 0, 1 as output binary output up to n number of strings, and this is Simon property. So what is Simon property? So according to this, each and every colliding pair which will belong to A bitwise addition B equal to R. So this is the Simon property. Our goal is to find this R. Our goal is okay. So for an example, take input A and we are giving to a function f of A. So if you are giving 0, 0, 0, if you are giving 0, 0, 0, it will produce 0, 1, 1. So if you are giving 0, 0, 1, it will produce 1, 0, 1. So you can easily find out for each and every input and output, you got an pair. So green to green, red again to red, blue again to blue. Okay. So violet again to violet. So this is colliding pair A comma B. So what is the answer when they are equal to 101? You able to find all these two. Okay. So if you want to solve any quantum algorithm, first you try to solve with classical. If you try to solve with classical, you know what is the problem happening in classical. Okay. To solve a Simon problem classically, one need to so this is the input and output function. Take an example of A 0, 0, 0, f of A 0, 1, 1. Okay. So when the collision will happen, take an example of R. Okay. R is 101. Okay. So whenever R is 101, you are able to happen only this collision. A not equal to B. So remaining every pair, you need to have the same to same. Okay, I'll share this material or after sometimes you watch through YouTube or your Canvas, you're able to understand. Okay. So the idea is for each and every input, you have same sequence. Take an example of 0, 0, 0, 1, 0, 1. What is the f of a? 0, 1, 1. Are you able to see the same input? Okay, thank you. So to solve Simon's problem classically, one needs to okay from network issue. So we can see from Simon words, this might not be true. This might not be true. The previous slide. Okay, we'll explain previous slide. So this is about solving algorithm classically. To solve Simon's problem classically, one need to find two different inputs of x and y for which f of x equal to f of y. Since one can determine if s equal to x bitwise addition of with y, where addition is done bitwise mod 2. Okay, mod 2 means bitwise. Otherwise, show that no two inputs produce the same output. Okay, so according to the Simon, this might not be true. It's possible that there is some magic algorithm that can always find the string s efficiently, but somehow routing around the details of computation of f. So most of the time in quantum, it is based upon the probabilistic, based upon the random effects. Okay. So however, we abstract away such hypothetical solution, which are almost never found, but almost never proven impossible by expressing f as an output, which leaves finding an actual pair of inputs with the same output as the only path of finding s. So it might be a little tricky. Let's say in very simplest way. So the natural approach is we need to do a random search because we cannot find sequentially. If you go sequentially, it will take exponential time. So classically what we'll do randomly. So randomly search for a colliding pair with m queries. So each and every time you need to query your table to identify whether the given pair is colliding with any other pair. So this is the logic. So choose A1, A2 until A of m, which belongs to 0, 1 to the power n randomly. So we need to do each and everything independently, not in sequential way. So if you do so, for all j not equal to k, okay, if E of j not equal to E of k and f of aj equal to f of ak. So this is the condition given in the algorithm. Then the output E of j modulus bitwise addition E of k, and we need to halt. So this is the generalistic natural approach, we need to do classically, right? Then we can ask question that how big should M be for the probability of a collision to be a constant? So that 3, 3, 4, right? So each pair, so whenever if you are giving any input and probability, amplitude. So what is the probability amplitude of Simon's algorithm? It will give 2 power minus n. It will give 2 power minus 1. Is it clear now? Hello. Is it clear now? Hello. Am I audible now? Yes. Thank you. Thank you. So it will lead to approximately m square pairs. It will lead to approximately m square pairs. Therefore, for each and every constant collision, it will lead to root 2 power n probability. So if audio is not available, please rejoin. Try to rejoin. It is a frequent problem. Okay. So if any classical algorithm try to solve Simon problem, must take omega to the power root of 2n. Okay. So all classical best algorithm will require these many queries. Okay. So if you want to implement classically, this is the Python code. So we'll see code one by one. First, we need to import a random function and we need to define XOR, bitwise OR. So what is the first input? A. What is the second input? B. So we need to do XOR between A and B. Okay. So whenever you got input A, input B, we need to check whether both are equal. Okay. If it is equal, it will return 0. If it is not equal, it will return 1. Okay. This is about parity between two inputs. For an example, if A is 0, B is also 0. So what we will do, whether 0 equal to 0, it will check. Okay. So this is A of I. Imagine this is A of I. This is B of I. Okay. So according to this, this is true. True means it will return 0. It will return 0. I'm showing Python code. Oh, wait a second. Is it visible now, Python code? Hello? Visible, yes? Okay. So I try to explain from first. Okay. So the first line is import random. So we are importing the random module in Python. So line number 3, you can see we are defining a function. So this is function definition. So what we are defining? We are defining a XOR function. So what this XOR function will do? It will do bitwise addition. So make it simpler. Okay. So the first input is A. The first input is A. The second input is B. Okay. Now what we are doing, we are checking whether A of phi equal to B of phi. So suppose if A of phi equal to 0, B of phi equal to 0, then we are substituting these values over here. So 0 equal to 0. So this is true. 0 equal to 0. This is true. Then it will return 0. So this is what happening over here. So this is what happening over here. So this statement will return 0. Suppose if A of phi equal to 1, B of phi equal to 0. Now what happens? It will check 1 equal to 0. So this statement become false. So false means it will go to else part. So in else part what we are returning 1. So this will return 1. Okay. So just make a note. So any doubt within this thing you can ask me. So whatever you are giving input according to the entire length, it will do return of 1 or 0. Is it clear? Shall we move? Voice audible, slide visible? Great. So next what we are doing, we try to generate Simon function. So here we are giving two inputs. One is N, one is S. Okay. So S is our secret string. So S is our secret string. So S is nothing but secret string. So we need to identify the secret string. Okay. So for that, what we are doing, we are generating a function f of 0, 1 until n number of bits, which will be able to generate 0, 1 up till n number of bits. So this will satisfy Simon promise if f of x equal to f of y, only if x XOR with y equal to s or x equal to y. So in any of these two conditions, okay, if any one of these two conditions, it will yield f of x equal to f of y. So for this, we are doing two things. One thing is we are doing mapping all these inputs. Okay, so this time again, what we are searching all the bits for n. So whatever the input you are giving, each and every input contains two possibilities. Either 0 or 1. Okay, we are checking all these conditions one by one. So whenever if we are giving any input that is stored in the format of x and x is mapped to each and every output like in the previous table, right? So previous slide, this one, we are generating a Simon function. So for Simon function, we have two inputs. One is n, one is s. S stands for secret string. And this is about the algorithm. So we try to map each and every input, okay, each and every input which is called x, and we are doing XOR with s. So this is the XOR operation. This is XOR operation, or you can say bitwise addition. Bitwise addition. So how we need to do? We need to generate a random bits. We need to search in form of y. Okay. Again, we need to check each and every y which is exactly mapped in your x. So we need to do each and everything. Finally, we are able to find mapping. So this is the algorithm which will be able to do classically. So here what we try to do, we try to create that map and we try to check whether it is equal or not. Okay, whether if it is equal, each and every value, it will return your secret string. Okay. If there is no collision, it will return 0. Okay. If any collision is there, if any matching pair is there, it will return function with the help of comma n. So n is is my screen visible now? Are you able to hear? I reshare. Wait for 2 seconds or 3 seconds. Now is it visible? Thank you. Thank you. So sometimes if network structure, please refresh. Otherwise, I will refresh my site. So no issue. Shall I explain from this? Are you able to follow this slide? Okay. So all of you able to understand this one? First slide. Shall we move to next? Okay. Thank you. So no issue. I will do from first. I will do from. We will execute. We will execute. Okay. No issue. I will explain one more time. No issue. So we need to import a random module. So it will create a random inputs. It will create a random input value. Okay. So if you're doing anything random, classically, it is always pseudo random, not true random. Okay. So you cannot create any random number using classical computer or any classical algorithm. It is always pseudo random. So what we are doing, we are defining an XOR function. So line number 3 is function definition. Function definition. Okay. So yes, but classically you cannot create true random. Okay. Only by using quantum you are able to generate true random number. Okay. So this slide especially for classical implementation. So stick to pseudo random. So that is what I suggest. So this XOR function contains two inputs. So this is first input and this is the second input. Okay. See, these two inputs able to create a string. Okay. Suppose if a of I equal to 0, if b of I equal to 0, imagine like this. So substitute I equal to 1 more exactly. So a of 1 equal to 0, b of 1 equal to 0, then it will check these conditions. Okay. So 0 equal to 0, this statement is true. If it is true, what it will return? It will return 0. It will return 0. Okay. The another case, if a of 1 equal to 1, if b of 1 equal to 0, it will check 1 equal to 0. So this is false. So false means it will return 1. So this is what happening over here. So whatever the input you are giving, okay, for A and B, so it will check one by one. So example, this is A of 0, B of 0, this is A of 1, B of 1. So what is the value of A of 0? 0. What is the value of B of 0? 0. So this will compare these two, and what this function will return, it will return 0. So what is the case of A of 1? 1. What is the case of B of 1? 0. So this will compare these two, and what it will return? It will return 1. So algorithm behaves in this way. So this is n number of bits. This is n number of strings. So that is what it mentioned, length of A. So whatever you are giving, it will check bit by bit. Is it clear? Any doubt? Fine? Okay. So look at the next function. We are generating Simon function. So Simon function contains two inputs. One is n-bit string and one is S secret string. So this is your input. This is the secret string, which is hidden in your table. In your given table by your black box function. So our ultimate aim is to find this. Our ultimate aim is to find secret string. Okay, so for that we are creating two important aspects. One is mapping table and one is output. So we are generating set by set answers. So for that, what we are doing a format table. Okay, so whenever if you are giving any input, that is stored in X. So X is try to map with the given input. So it will do XOR with X with S. No issue. So this is function because I can, this is function definition. This is for loop function. So if you're not familiar with Python, just observe. I will share this code. You will execute. Just give input and observe how it is working. So if you don't know any experience about Python, so ignore both this implementation. At least try to understand, right? So it will do XOR function, right? So each and every time it will generate random bits. Yes, audio signal is clear. Audio is clear, I think so. So it will generate random bits for Y. It will do XOR. It will create a mapping table. So it will create a mapping table in line number 25. Okay. Then it will do XOR with X, XOR with S. It will generate Y as the output. That will happen during line number 26. So this will rearrange a table. It will do X XOR with S and it will store under Y. So this is how it will rearrange your table. Okay. So finally, this map is written to your input string. And this is the function definition to find S classically. So it contains two inputs. One is n string, which is the another one is function, your black box function. So we need to find each and everything with the help of brute force. So what we'll do, we'll compare each and every pair. Each and every pair, we try to compare with remaining pairs. So this is done by brute force, which is nothing but comparing with all possible combination, all possible combination. Okay. So what is the condition we need to check? Whether x not equal to x of previous one. If it is so, it will do XOR. So S is your staker string. So S is your staker string. If X is not able to match with previous XOR. Okay. So if there is no collision, it will return 0. So this is the logic. So how to execute this function? How to execute this algorithm? You need to define a main function. This is main function in Python. Main function in Python to execute. Okay. So what is the input? You are giving n equal to 4. What is the secret string? S equal to 1010. And how we are executing this function? We are replacing this n with 4, s with 1010. We are providing all this input to previous function. And this will return some value. This will return some value to f. Again, we are passing this f to another function. So this will find the final result. Final result. A string is found, it will display. A string is found, it will display. So go to QT. I'll share that link to you. Go to this website, QT. Okay. Where to find? Yes, I am looking for chat box. So go to this link. Yes, sir. So go to this link. We will rejoin after 5 minutes.